This is the Schneider DP200. The DP stands for Digital Projector, the 200 the horizontal size of the XY stage. It replaces the shadowgraph, which has been used for many decades to project a silhouette of a component onto an opaque screen for inspection and measurement. The DP200 is a digital camera system that views small areas of a large XY stage. The range of the XY stage are available from 200 by 100mm, which is the one being demonstrated, but there are also a 300 by 200, 400 by 200 and 500 by 200mm options. Because the digital camera looks at a small portion of the whole surface being inspected, a range of objective lenses are available, one of which will be specified when ordering. Because of this, the view areas vary from 4.3mm by 3.4mm up to 26.5mm by 21.2mm in 5 convenient magnifications, depending on your application. This system has a 13.2mm by 10.5mm objective lens, which is the mid-range option and addresses a large portion of the applications we see. Because you only view a small portion of what could be a large component, the XY stage is movable anywhere in its range and is fitted with a dual Heidenheim grating with 1 micron resolution, which means you can accurately assess large geometry to high accuracy. The table also has a stainless steel surround with double T-slots parallel with the direction of movement. This enables easy fixturing. The optical system is telecentric, which means the focus on the surface of the plate and above the surface is parallel, meaning a slip block will show the same result on the bottom and the top surface. There is no optical distortion. This is a major feature of the Schneider DP200. Today, behind all good instruments is powerful software, but this is not only powerful, it is simple. This means you do not need a skilled operator in a metrology laboratory. This is an instrument that needs little more than 10 minutes training and is as useful in the inspection room as on the shop floor. Let me show you what it can do. The screen is free of words, just simple icons. In the top right hand corner is the X, Y and angle position. These can be either absolute values or relative for easy point-to-point dimensioning. If you want to crosswire, press the icon. If you want reference circles, press the icon. If we want reference geometry, we can select a chamfer, we can select a fillet, we can select an angle, or a diameter of any size. On chamfers, we can move them through 90 degrees. And exactly the same for fillets. On angles, we can select the specific angle you require and again move them around by 90 degrees. Let's look at a typical measurement problem. Not putting the component on square introduces errors. If we take a slip block, if we measure it here, we get the correct answer, but if we measure it here, it is wrong. Let's put the component on incorrectly. So we first of all put the component intentionally wrong onto the surface, and we align the first edge and zero our X and Y coordinates. Then we can move the slip block to the other edge. We can now line it up onto the second edge, and you'll see in the X value there is more than 0.5 millimeter error in 30mm. So now we're going to teach the system the angle at which the component's been put on. First of all, we align a point which becomes a pivot point. We can then move across to teach the system the angle at which the component sits, and now rotate the coordinate system according with how the component sits on the surface. Now that we've taught the system the orientation of the component, we can align onto the first edge and zero the X and Y coordinates and go to the second edge. And because the coordinate system is in line with the angle of the component, you'll now see that the error is only a few microns. Okay, so I only found that by eye, but everyone has a different opinion when judging things by eye. But this is a software system, so we can use an aid to automatically detect the edge, the difference between the black and the white. There's a green line indicates that point, and as we accelerate in towards it, a line comes in a red line and tells us how close we are to the intercept. Once it's aligned, it turns green, and we can zero the X and the Y coordinates. By going to the opposite edge, the edge detection will automatically see the difference between the black and the white silhouette, and again a red line will come in from the edge, getting closer and closer until it turns green at the exact intercept. Let's take a look at this demonstration component, which has a series of holes, angles and blind slots. The component you are measuring is usually of a known design, and we used to use overlay template drawings on the shadow graph screen. But now, if you have the outline shape on CAD package, you can export the DXF file to be used as a template for comparison. Once we've loaded the DXF file of the template, we can align the component to the origin of the DXF 00 and set this as our datum pivot point. You'll now see that the template is on top of the profile, but we can see that the component is not square with the origin. So once again, we can teach it the angle at which the component is set and then rotate it to align the DXF with the actual component. By using a pin, we can do a fine adjust so that the template and the component are overlaid with each other. Then we can see around the profile any error, departure from the template. Well, that's about it in terms of what you can do with the geometry of the surface, but being a digital camera system, you can switch on a top light and see details which you would never see with a shadow graph where the light cannot pass through. And you can repeat all the geometric measurements which have just been done with a shadow graph now on hidden detail. For any further information, please visit our website at www.spectrum-metrology.co.uk.